This video is dealing with the first part of section 5.3, conditional probabilities. All right, so sometimes we want to discuss a probability that something happens given that we know something else or some other event has already happened. And this is exactly what we mean by a conditional probability. So it's the probability that some event happens given that we know some other event has already occurred. All right, so the probability that one event happens given that another one is already known to have happened is called a conditional probability. So we use a certain kind of symbol to denote this. And so we see here down below here, we see probability that B happens given, that's what this little vertical line means, given that A has already happened. Okay, so that vertical line generally means given that. And so the second thing listed is the thing that has already happened. I know it kind of sounds maybe like a little backwards. It seems like you would list the thing that's already happened first, but it's not. So really, ultimately, we're trying to calculate the probability that B is going to happen. So that's why we list it first. So if you're looking at that, it's the probability that B happens, but it's given that A has already happened. And we have some formulas here, and these formulas really won't make sense until we later on in the section when we kind of do some algebra, and we'll be able to rearrange them later on in this chapter. So if we have the probability of A given B, again, that's the probability that A is going to happen, but we know that B has already happened. So we know that that's equal to the intersection, the probability of A and B happening, so both happening, divided by the probability of B. And then if we reverse it, the probability that B happens, given that A already happened, it's equal to the probability that both things have happened divided by the probability that B has happened. So these two things, probability of A and B and the probability of B and A, those are the same. It doesn't matter which order we put the two things if we're talking about an intersection. Okay. So let's look at an example. Sometimes we'll be dealing with conditional probabilities in a two-way table. Okay, so first, these are 10,000 grades at a university. The university has 3 schools in it. It has a liberal arts, it has an engineering and physical science, and it has a health and human services. And then, so we've classified the grades based on what school they were given in, all right? And then also what kind of grade it was. Was it an A, a B, or was it below a B? All right, and further, we've defined some events. So event E is that the grade comes from the engineering and physical sciences department. And L is the event that the grade is lower than a B. So if we randomly select one of these grades, the first thing we want to do is calculate the probability that L has happened. So the probability that the grade we selected is lower than a B. So first thing we want to do with this table is come up with the marginal totals. So the column and the row totals, and then of course the table total of 10,000. So we're dealing with 10,000 grades here. What's the probability that I randomly choose a grade and that grade is below a B, which is what event L is? So the first problem there. If you look, there are 3,657 grades that are below a B. And so we simply take that and divide it by the 10,000. So that's the probability that the grade is below a B. There's 3,656 grades below a B out of the total of 10,000 grades. So that is about 37% of the grades are below a B. All right, the next one is a conditional probability. What's the probability that E it happens given that L's already happened? So in other words, we know the grade is below a B. L happens. We know that's true. So we know the grade is below a B. Now what's the probability that the grade is from the engineering and physical sciences department? All right, so a way of looking at this when we're dealing with the table is that we know we're in that column below a B. So we're in the yellow highlighted column, and so we can see that it's simply the 800, which is the number of grades that are below B that came from the engineering and physical science department. So it's simply 800 divided by that column total of 3,656. All right, and then the last one is we reverse it. What's the probability that the grade is below a B, given that the grade was given from the engineering and physical science department? So this time we're going to be looking at being in that row. So we're in that engineering and physical science row. So we know we have a total of 1,600 grades, 800 of which are below a B. So the conditional probabilities are pretty easy to use if we're dealing with a table. We simply know that we're dealing with either all the grades that are in a row or all the grades that are in a column. Let's look at some of the calculations that we could do using our formulas. All right, now we just want to test that our, basically show that our formulas would work. So the formula at the top right corner here is the probability of A given B is the probability of A and B happening divided by the probability of just B happening. So if we apply that formula to what we're trying to look for, the probability of E given L, we could apply it and say that the probability of E given L is the probability of E and L divided by the probability of L. And so the probability of E and L, that would just be the intersection of E being the engineering row and below a B column, which would be 800 divided by 10,000. And then the probability of EL, we've already calculated in the last slide. That's just simply this column total divided by the table total. And now if we go back and look at this, then we can see that the 10,000s will cancel and we get the result that we were expecting, which we calculated in the last slide. So this calculation is the same, close to 22% that we saw in the last slide. But it's really just, we're just trying to show you that the formulas do work. Now, formula is a little bit more, more complicated way to calculate this problem. The original problem that we calculated in the last slide, that's easier to calculate just looking at the table, knowing that we have 800. We know we're given L, so we know we're in the below B column, and we want the engineering, so that's 800 divided by the total of 3,656. Okay, so it's just easier to calculate using the table and not the formulas, but sometimes the formulas are useful. Basically, just trying to show you here that the formulas do indeed work. All right, so if we do a little bit of a manipulation of that formula that we were just using, we can isolate the probability of A and B by itself by multiplying both sides by the bottom of the other side of the equation. And so we get the probability of A and B happening is kind of makes sense here. If you think about it, it's the probability that A happens and the probability that B happens, but given that A has already happened. So it's the probability of A times the probability of B. This is what we call the general multiplication rule. Okay, so in order for both events to have happened, the first one's got to happen, and then the second one happens given that the first has already happened. All right, let's look at an example here. we're flipping a coin, and we're going to practice using a tree diagram here. So we're flipping a coin, and so you can see the first sort of nodes are the first event, flipping one coin, and then the next nodes are kind of the results of the second toss or the second event, tossing the coin again. All right, so if we want to know what's the probability of getting two heads, well, we would have to go through this branch because we get a head and then another head. And so when we want to know what's the probability of two things happening, we simply multiply through by multiply the probabilities for each of the branches. So another way of looking at this is, well, there are four possible outcomes, right? We could have head, head, tails, tails, heads, and tails, tails, each one equally likely. So we could think of it as 1/4 as well. So one outcome out of four, each equally likely. That would give us a probability of 1/4. So there's a couple ways to look at this. You could think of the sample space, or you can think of this tree diagram. All right, let's look at another tree diagram example. The Pew Internet and American Life Project finds that 93% of teenagers, that's age 12 through 17, use the internet, and that 55% of online teens have posted a profile on a social networking site. So that 55% is a conditional probability, right? Given that the child or the teenager is online, there's a 55% chance that they have actually posted a profile. So that is a conditional probability. Let's look at that on a tree diagram. All right, so you can see first here we have the first set of branches. First going this way, 93% of students are online. So we ask the question, is the teenager online? Yes, 93%. No, going down here, and that's 7%. So each of these branches from each of the the beginning node, those two things have to sum up to 100%. Now you could have more than one branch, but in this case we're asking yes or no questions, so we only have two branches. But all of the branches from a particular node should add up to 100%. Okay, so now they told us this conditional probability up here that 55% of online teens have posted a profile. So that goes here, right? So given that, yes, you're online, 55% of them, yes, have a profile. So that 55% is a conditional probability. So these second branches are always conditional. So this 45%, that's a conditional as well. So what's the probability that they don't, if we randomly select a teenager, what's the probability that they do not have an online profile given that they are online, right? So this is a conditional probability. That the probability that they don't have, no, they do not have an online profile given that they were online already. Okay, and then down here, these are a little bit silly because it's if obviously. What's the probability that you have an online profile? Yes, if you are not online. So that's of course a 0%. You can't have an online profile if you're not online. And so what's the probability that you do not have an online profile if you are not online? Well, that's 100%. All right, so it's kind of a little bit of a silly example, but all right, so let's calculate some things. All right, so what's the probability that you're online is 93%. The probability that you have a profile, given that you're online, that's the second branch. That's a conditional probability. That is 55%. All right, now, what's the probability that you're online and have a profile? So that's going to be the product of those two things. We're going through that branch, to yes, you're online, and continuing on to the yes, you have a profile. So that would simply be the product of these two things, right? If you go through all of the branches, there's 4 different routes that you could go through this tree diagram. That those results would all be the intersections of yes, you're online, and yes, you have a profile. All right, and so we would simply multiply those together. So the probability that you're online and have a profile, we would simply multiply those two together. And we're using that formula, that general multiplication formula that we were just talking about. So the probability that you're online and have a profile, well, what would you have to do in order to have that happen? Well, first, you have to be online and you have to have a profile given that you are online. So it's the product of those two things. Let's look at all four of those branches as we go through. Okay, so here we are. What's the probability that you're online and have a profile? That is simply the product of the two probabilities going through that branch to get to yes, yes. All right, and that's the one we just saw. All right, but let's look at the other three. All right, so what if I say what's the probability that you're online and don't have a profile? That would simply be the product of those two. As you go through those two branches, you would just simply multiply those together. All right, and then the next one, what's the probability that you're not online and have a profile? Well, if you're not online, obviously you're not going to have a profile, and so it's not surprising that that is 0, but it's the product of those things as you go through. 0.07 times 0, which of course is 0. And then the last one is what's the probability that you're not online and do not have a profile? So that's simply the product going through those two branches. 0.07 times 1, which is 7%. Now, it's probably shouldn't be surprising that there are 4 possible outcomes. The probabilities of all 4 of those added up will equal 100%. All right, so now let's think, instead of a tree diagram, let's think of a two-way table. So the top is one possible question. So let's start on the side. So do you have internet? Yes or no? And then the next question is at the top. Have you posted a profile? Yes or no? So just like when we were going through that tree diagram, there are 4 possible outcomes. Here in our two-way table, there are 4 possible values inside. And so those values are the intersections. So the probability that if you randomly choose a student, probability that yes, they're on internet and yes, they have a profile, those are simply those 4 intersections in the middle of our table are the 4 values we just calculated. All right, so that's the 51%, the 42%, the 7%, and the 0%. Okay. And so to make your table, it's a little bit more complicated to make your table because you essentially have to do the multiplications through the tree diagram to get those values in the table. Of course, once we get those values in the table, we can do our marginal totals pretty quickly. And then it's a little bit easier sometimes to use your table. You can answer more questions and do it more efficiently once you've established a table. The tree diagram has some limitations to it, as we'll see. We'll look at another example in a second. All right, so let's answer some questions. All right, what's the probability that you have internet, that you're online, and you have no profile? So again, that's an intersection. So we just find the row, which is yes to internet, and the column that is no to profile. And we look at what number is in the intersection of that row and that column. Oh, actually, I'm using the formula in this case. You can, but it's just easier not to use the formula in this case, but easier to, we've already done this. I've already multiplied these things together in the last slide. So it's just easier to look at that value, right? And then this table, unlike the example that we were looking at before, sometimes have counts in them, but here these are probabilities. So like the grades, we were talking about 10,000. So we would take the value divided by the table total, but here we don't have to do that because these are percentages already. And so that's not a coincidence that that 42 is the intersection of that row that is yes to internet and the column that is no to a profile. So we don't have to really use this complicated formula or to multiply these things. Look at all these two different probabilities and multiply them together. We can just steal it right off the intersection of that. All right, what is the probability that a randomly selected student has no internet given that they have no profile? All right, so the given part is no profile. So that means we are in the no profile column. All right, so now what is the probability that they have no internet? All right, so in this case, it's the, it's this number, 0.07 divided by 0.49. The probability that they have no profile is going to be the 0.49. Probability of the intersection, that's this intersection of no internet row with no profile column. All right. And again, so that's pretty easy to do just from the table. You almost don't even need this, because if we are the formula, if we know we're given no profile, I know I'm in this column, and so it's simply the ratio of no internet over the column total percent, which is 49%. All right, so if we look at it this way, it's a little bit easier than using the formula. We know we're in, that given tells us we're in that column. And so we simply look at those two numbers, and it's the ratio of those two numbers. Okay, so you can certainly use the formulas, but a table sort of allows us not to have to rely on the formulas and instead just get comfortable pulling the numbers right off the table. All right, let's look at another example. So here we're going to make a tree diagram and a table. Generally, we make the table from the tree diagram, but once you have a table, then the calculations are pretty easy. They can't really ask us any questions that are too hard to do. So tennis great Roger Federer makes 63% of his first serves. This is in the 2011 season. All right. When he made his first serve, he won the point 78% of the time. When he missed his first serve, he had to serve again, and he won the point only 57% of the time. So we'll use that to kind of make our table. So the first branch is in our table, this branch, and this branch will have the percentages on it, right? The percentage, and in the box we'll write what the event is that happened, like what happened. So did he make his first serve? Did he not make his first serve? All right, so 63% of the time he makes his first serve, 37% of the time he misses his first serve, because we know these two numbers have to add to 100. Okay, and so then what do they say? When he made his first serve, okay, so we know he made his first serve. It's a conditional probability then. So he wins the point sometimes, he doesn't win the point. And then when he misses his first serve, he sometimes wins the point, sometimes he doesn't win the point. Okay, so fill in these percentages here. So what percent goes up here? So in other words, given that he made the first serve, what percent of the time did he win the point? All right, and so that was that 78%. So as a result, we know this has to be 22 because the two have to sum to 100. They typically don't tell you both of those, they just tell you one. And then the other one says he won the point 57%. So he won the point 57% of the time when he missed the first serve. So again, that was a conditional probability. That goes here, 57%. So as a result, these two things have to add up to 100. All right, so now knowing those things, fill in the tables. Remember, these four numbers here are the intersections, which are the product of the probabilities as you work through the four pathways on our tree diagram. All right, so if I multiply 0.63 with 0.78, if I multiply this together with this, I should get yes to both, this one, right? All right, and then if I do yes, he made the first serve, but no, he didn't win the point, then that's the product of the 0.63 and the 0.22, and that should give us yes, he made the first serve, but no, he didn't make the point. That should be this value here. All right, so just like we did in the last example, you'll fill in that table's intersection values, that's inside the body of the table. Those four intersections are found by multiplying through your tree diagram. All right, and then of course the marginal totals simply get added up, the top column totals and row totals. All right, so now let's answer some questions about Roger Federer's tennis. So what's the probability that he wins the point given that he made the serve? All right, and so that one, that is a conditional probability, and that one's actually easier to calculate looking just right here, okay? We would, if we were using the table, this one actually is a little bit more challenging because it's like, okay, makes the serve, so that means we're in this row, and so now we have to divide probability that he wins, so it's this 0.4914 divided by the 0.63, but it's a conditional probability, and we can pull that off right up here. Okay. That's probably the easier way to do that. All right. So the probability that he wins the point given that he makes the first serve is 78%. It's always good to answer your questions in the form of a sentence. All right. So we can also look at it here. And we can calculate that by looking at that, the given, which is he makes the serve, looking at that row. Okay. Let's ask, what's the probability that he makes the serve and wins the point? All right, so we can think of it as the product through, right? Makes the serve and wins the point is an intersection, and so we can think of it as the table. We can multiply through the tree diagram, I mean, and simply get our answer. But of course, we want to also think of it as, well, it's just the intersection of yes makes the serve, yes wins, and so it's the 0.4914. Okay, so he can do it. You can do that either way there. And again, we want to write it in the form of a sentence. The probability that he makes the first serve and wins the point is 49%. All right, let's ask ourselves another question. What's the probability that he wins the point? Well, there's two ways that he can win the point. If we're looking at the tree diagram, he can make the first serve and win the point, or he can miss the first serve and win the point. And so whenever we hear the word or in statistics and probabilities, it's always adding. So we could add up those two probabilities. So it would be the product of the two pathways through, but then we would simply just add those up. Okay. Another way, it's not a coincidence, though, that value is sitting there right on the table, right? So the probability that it wins the point would be just that 0.7023. That's the bottom of, or the total in the column of, yes, he wins the point. All right. And the other two numbers that we found when we multiplied through, obviously that value and this value already in the table. I mean, indeed, that's how we got that table. We got them by multiplying through each of the pathways. All right, so Federer wins the point 70% of the time. All right, let's look at one more question. So assume that you're watching the tennis on TV and you get distracted, and then you look up and you see that he wins the point. Now, what's the probability that he missed the first serve? So this is a little bit more. This is a conditional probability, but it's not one of the conditional probabilities that's listed here. It's kind of a reverse. So what's the probability in symbolic terms? What are they asking? They're asking what's the probability that he missed the serve given that he won the point? Like I saw him win the point, but I missed the first part of the volley, and so I don't know if he missed the first serve or not. All right, so we can use formulas for this. And so it's probability that he missed the serve and wins the point divided by probability that he wins the point. So the top is just gotten from multiplying through that pathway. And then the bottom is gotten from, again, multiplying through two of the pathways. We just calculated that value in the last question was what's the probability that he wins the point? There's two ways that he could win the point. All right, and so we simply calculate that. Now, going to the table makes this problem very easy, right? Because we're given that he wins the point. So we know we're in this column. We're in the yes, he wins the point column. And what's the probability that he missed the serve? All right, so we simply take the no, he didn't make the first serve divided by the total in that column. And so this problem is so much easier to do with a table than with a tree diagram. All right, but we get the same value either way. We sort of already did the work of the again making the table by multiplying through all the values in the tree diagram. So that's kind of why the table is easier to use because you already did the work. All right, this is your assignment for this part of section 5.3.